Previous video we looked at radical reactions, where we saw two mechanisms that are actually competing for various products that are being formed. One is looking at combination versus that of the disproportionation reactions, and in this video we're going to see how a radical will actually react now with a molecule that is really stable. There is no form of loose electrons, or if there's charge, the charge is actually stable in that particular state. But in this particular molecule, we're going to see how these radical molecule reactions will actually result, surprisingly, due to interesting statistics, to formation of a more stable radical. And also there are noticed to be 4 ways to actually arrive at this particular process. Now the first one in here we're going to look at is the atom transfer, where we're going to focus on a particular atom being removed from one particle molecule in here to another, and this is also called an abstraction process, like we saw in our previous video, where we looked at how abstraction from one molecule to another leads to the formation of a radical that will enhance more reactions in the process. Now one case scenario is actually, I would say, adding to this, is that we can do that with hydrogen atoms, or that of, I would say, halogens. And halogens in the sense that we look at the group 7s, which are fluorines, the chlorines, the bromines or iodines in there, extracting those from one particular molecule to another, because they are actually good, I would say, electronegative compounds. And now we can actually focus on hydrogen, and you can actually extend it to these particular molecules, which are the halogens. Now first one in here we're going to look at is tert-butyl, which is a compound, and this actually has oxygen, which is a radical, and this is going to be subjected to a phenyl, which has a methyl group attached in there. I'm going to expose this hydrogen right here, and what we recognize from this particular mechanism from here is that we have the oxygen radical actually causing the taking of a hydrogen here and the breaking of a bond to actually form alpha carbon on this particular species, and this results in the formation of our product, which is the tert-butyl hydroxide, and that of our methyl phenyl radical right there. So in this particular case, the one contributing factor to the forcing of our reaction further to the right side is based on the thermodynamics, where we look at the carbon hydrogen bond to actually be broken, and this breaking of the bond leads to an endothermic process, which is positive 0.4 kilocalories per mole, and this compared to this other particular species that is being formed with the hydrogen oxygen bond formation leads to the release of a bond, or energy, sorry, which is about 110 kilocalories per mole. So in this particular case, when you will compare this, the overall reaction in here is known to be an exothermic process in here, and this is actually driving force for the moving of our reactants over to our product. So that's about it for this particular first step in here. Another one that we can actually add is looking at alpha carbon attached to this particular 2 methyl groups right here, and this is attached to a hydroxyl, and this is going to be subjected to oxygen gas. And what we notice that this oxygen gas is actually going to cause the abstraction of this hydrogen, and this leads to the breaking of a bond to actually form a pi bond on this carbon, resulting in the formation of a carboxyl form, which is a ketone, and monohydrogen peroxide right there. So these are actually the 2 ways by which we can actually engage hydrogen in terms of oxygen picking up the hydrogens to actually form stable radicals right here, either due to resonance in here and also the formation of our stable molecules. So that's about it for the first part, and the second one in here is going to be looking at the idea of involving our pi system in terms of the addition process. And in terms of the pi systems, a typical example is polymerization, and polymerization in here for the case of this particular video is looking mainly at violin, and violins are, I would say, in this particular nature where we have double bond on these carbons, and what that results is that one position in here is where we have our R group, and this R group is actually going to be involved in various of the functional groups attached in there to, I would say, increase the functionality of these violins. For the case of this video, we're going to have I would say phenyl group attached as the R group to this carbon, double bond carbon right here, and this is going to be subjected to an ethyl radical. And what we recognize from this particular reaction is that there are actually two ways to actually arrive at different products. Now, one way is actually going from the top, where we actually get this carbon to be engaged by the formation of a bond here, and here leads to the formation of a radical right on this carbon, while on the other side we get the other radical actually engaging this compound in terms of this carbon forming a bond here, and here resulting in the formation of a radical right on the end of this carbon. So what that results in this B part is radical on this carbon which has a C2 on it, and this actually is actually loosed when you're forming a CH here, and we have a phenyl attached right there, and on this other side we have our CH2, CH3, and while on the other side we have our other product, which is actually having our phenyl group, and this is attached to a carbon CH, and this is actually a radical, and on one side here is that we have our CH2, CH2, CH3. Now the big question is A our major product, or is B our major product? And from various analysis, what they figure out is that A is actually our major product, and the reason is because that first we have high numbers of carbons actually surrounding our alpha carbon. So what that results is that inductive effect causes the stabilization of this alpha carbon with respect to the electron on it. And secondly, we also recognize that we have less sterics during this particular ethyl radical attacking this particular exposed, I would say, carbon, thereby forming a bond easily, which is a sigma bond, rather than actually doing that on the B section of our mechanism. And finally, we have a case where we have interesting resonance that actually makes this particular compound to be more stable compared to this particular compound right there. So therefore A is more favorable than B. And also we're going to have another, I would say, reaction here, which is where we have CH3, CH2, and this CH2 here is a radical right there, and this is going to be reacting with oxygen gas again. And what we see is that this oxygen gas does actually form a bond in here with this particular alpha carbon, and this results in the formation of our product, which is just one product, where we have CH2 with the oxygen, and this oxygen is actually radical right there. And this particular product here is actually highly detectable by antioxidants in the body. So therefore we can't actually detect this, or the body antioxidants cannot detect this ethyl radical, but rather would detect this one in here. And this is kind of important in terms of various interesting activities that we do that involves oxygen in the body. Now the third one in here we're going to look at, which is C, is looking at the electron transfer. This we're going to dive a little bit less in detail, but what we can say is that in this particular reaction where we have a carbon alpha radical right there, and this is a hydroxyl, and this is actually attached to a methyl group, what we see is that this is going to be reacting with, I would say, a methyl halogen, where we have nitrogen in this particular ring, and this nitrogen here is positively charged and attached to this, and we have this symmetry actually happening on the other side right here. And what we recognize is that this particular molecule that we're describing, for it to actually react with this particular radical molecule, we notice that this radical molecule is noticed to be electron rich, and this electron rich presence of this molecule makes it to be a reducing agent and causing the reduction of this particular molecule right there. So therefore this actually donates electron to this compound, thereby causing this to actually become electron poor, and also resulting in it being an electron acceptor, and resulting as well to the formation of our product, where we have our radical on the nitrogen, and while on the other side here we have this actually forming first our OH and C positive charge on it with our methyl groups on both sides. And then what happens next is that due to solvent effect, we actually have the breaking of this bond to form a carboxyl, and this results in the formation of a ketone right here, and also the release of a proton. So that's about it for C. And finally we have our D, which is a homolytic substitution, which involves a polyatomic center. And for the case of this video, we're going to use boron as the polyatomic center, which has, I'll say, ethyl attached on 3 sides of it. And what we see is that boron is actually known to be a good, I would say, Lewis acid. And what happened here in this case is that this bond cleaves off to actually make this electron to move to boron, thereby accepting the electron, and this results in the formation of an ethyl radical. While on the other side, this is going to actually be reacting with another, I would say, radical here, which is actually again third butyl oxide. And what that results in is that this third butyl oxide then forms a sigma bond with the boron, and this is also similar, I must say, to an SL2 reaction. So this results in the formation of our product, which is actually shown here, where we have our third butyl oxide, which forms a bond with boron, and we have our CH or ethyl compounds, and here we have our ethyl radical present right there. So that's about it for this video. Please hit a comment down below, let me hear your thought about this 4 ways or 4 reactions that can actually be involved in terms of radical molecule interactions and leading to the formation of stable radicals during these processes.